What do we need to make a robot? Well, we need two things, atoms and bits, hardware and software. It's easy to think about hardware. Those are the things that you can touch. To make a robot, you typically need these building blocks. You need actuators to move around or to change the world. You need sensors, which can be exteroceptive, to see the world outside, or interoceptive, to sense the state of the body. You need computation to run the code. You need comms to communicate with other robots and people. And you need some store of energy to power everything else. You need all of these to make a self-driving car. But there are many robots that don't need all of these. There are minimalistic robots that have no exteroceptive sensors and can perform a task while blind. Or robots that take energy from the environment, like a glider using thermals to climb up in the sky. Also, no robot is an island. It's better to think not of a single robot, but of a robotic system, which contains the robot and the environment around it. When you design a robot warehouse, you really want to make the robot itself as simple as possible by structuring the environment, for example, by putting localization markers on the floor. When you design a robotic system, you should also think about the interaction with other robots. You should think about the infrastructure that you have available. Do you have wireless? Can you access cloud computing? Can you use a data annotation service? The best results come from co-designing the robot together with everything around it. In many applications, the environment includes humans, like customers or teammates or supervisors. You cannot design the humans, but you should learn how they behave and their expectations about how the robot behaves. Let's now look at Duckietown. Let me introduce you to the Duckiebot and to the Duckietown. This is the Duckiebot. For actuators, it has two motors, two rotating wheels, and a caster. For sensors, there is a camera in the front, and there are odometry sensors that detect the rotation of the wheels. There are actually other sensors, and it's extensible, but those are the ones we're going to use in the course. For compute, there is a Jetson Nano, which has an ARM processor plus a GPU. For communication, we have Wi-Fi antennas and an Ethernet port. Finally, for the energetics, we have the smart Ducky battery. Let's now look at the environment, what we call Duckietowns. There are tiles of several types, and there are street signs. In some versions, there are traffic lights and watchtowers. There are precise rules about how the tiles can be configured and what signs can be used. That's it for the hardware, that is, the things you can touch. Everything else, let's call it software. By software, I mean, in addition to the computer code, also all the supporting information that a robot needs. For example, the traffic rules to follow in Duckietown, the specification of the task, or the prior information about the world and about the other agents and their behavior. Finally, there is data. Some components of modern robotic systems use learning. Critical to learning is the training data and how you choose it and preprocess it and update it. Robotics is a very deep discipline. To make a robotic system, you need everything else. But it is not as simple as choosing the pieces and putting them together. There is an art of how to choose components that work well together, or finding the best combination for a particular task. For modern systems, it's relatively easy to make the components, but hard to integrate them. This course is about single robot autonomy. That means we are mainly concerned about the software for one robot. The hardware is already chosen and the environment is specified. What's left to do? Let's draw a diagram starting from the line that we call the design line. Below we put the things that are fixed. There is the environment, actuators that take commands and act on the world. There are sensors that produce observations. What's left to do is above the line. We need to find out how to compute commands from the observations. For example, how to decide the wheel's velocities from the camera images. We will call what's above the line the agent, or controller, and what's below the line the world, or plant. How can we do that? There is no easy answer. It's a new discipline. What we know and we explain to you are several approaches that can be combined together to make autonomous robots. There are three fields that heavily influenced robot autonomy. The oldest is control theory, or cybernetics, which deals with low-level signals close to the hardware. There is classical artificial intelligence, which originated all the symbolic representation that a robot uses. Then there is modern machine learning, especially deep learning, with its data-based approach to solve problems. None of these three approaches alone can solve all of robotics or the problem of autonomous driving. If you look at the AVs deployed on the road, the companies behind them use a healthy mix of these. One of the goals of this course is to give you knowledge of the different approaches and advice on how to combine them. In this video, we introduced the hardware and software components of a robot. Also, we saw that no robot is an island. We should talk about a robotic system instead of a single robot. Finally, we declared that we don't have an easy answer to the question of how to make a robot autonomous, but we are very happy to bring you along on a tour of some of the methods that have been found to be effective.